Hiya. So in this video, we're going to look at these things called random scatters. And basically what it is we're going to use this Poisson distribution in order to tackle a common question. And we kind of started stating this before. And basically the common question is, if I have like a rooftop and it's raining and I'm trying to calculate the distribution of the raindrops. So you can think of this as raindrops hitting some sheet. We're really thinking of how many times a particle hits some surface. So whether that's raindrops on a sheet, that's particles like dust hitting something, molecules hitting photons, like just anything that's hitting something. You can also think of this as like positions in space. So like if you're looking at a microscope in biology and you're trying to figure out the position of different cells or organisms, in astronomy, you can think of this as positions in the night sky of the stars. You can even think of this in baking, like if you're making chocolate chip cookies and you want to know the positions of your chocolate chips inside of your cookie, right? So this is the type of distribution that we're going to be looking at in this video. So as you can see, this is a very big, there's a lot of different ways you can look at this. And this is very dependent on the fact that the number of points in a given area has Poisson distribution. So this is really where the Poisson distribution shines. It's how many points are in a certain area, whether that's in a plane, whether that's in a volume, whatever. So you can do this in higher dimensions too, 2, 3, 4, 5, 9, 37, 1,677. Like it doesn't matter how many dimensions you have, you can just go higher and higher. So we'll still have the Poisson distribution for regardless of anything. There are two kind of points that we do need to make in this. The first point being that we want to assume that no 2 points are in this exact same location, right? And this kind of works. Like think about it. In astronomy, you're never going to have 2 stars in exactly one same position, right? They might be really close, but they're never in one spot. You'll never have 2 chocolate chip cookies in this exact same position. Well, maybe after you've melted them and like eaten them, but you get the point, yeah? So like it's not too big of a jump to ask for something like this. Another thing that we want to assume is that there's an equal chance for the point being anywhere, aka it's random. Now, you might think, well, the universe, like when we look at the stars, they're not all in the same spot. But if we think about how the universe expanded, there is an equal probability that any one of these stars might end up in any location. And so this is what we mean by there's an equal chance for a point being anywhere. The probability of any point existing is equally likely because they all started from the same like nothingness, or ask an astronomer or physicist, they'll explain better. But anyway, started from Big Bang and they all had the same chance of going anywhere, right? Same with a cookie dough, right? Like as you're mixing it, you're giving the same probability that it might go anywhere. Now, this idea, the frequency of how many points will occur, is actually estimated by a constant. And this is what gives us what's called the Poisson scatter theorem. Poisson obviously coming from the fact that this is a Poisson distribution. So here we'll do the 2-dimensional version, which basically says if I have a square sheet, so I'm looking at some square area where there are no exact points in the same location, and all the points are randomly placed, right? So this is basically stating my 2 conditions up here, right? These are the 2 conditions that we're using. So this is 1 and this is 2. Now, if we let B be some subset of the square, and we let XB be the number of hits in B, then what we know is, 1, we know that XB is a Poisson random variable with parameter lambda times the area of B. So lambda is just some constant. We won't go into it right now. And we know that too, that if B1 and B2 are disjoint subsets, so if we have 2 different things, so here we might want to, so here's the little square, if B1 is here and B2 is here, and they're disjoint, they don't overlap, then XB1 and XB2 are independent events. Now, the cool thing, so this thingy coming from this lambda, because we haven't really defined this random scatter is actually called, is called the Poisson scatter with intensity lambda, right? And this lambda is really coming from the number of hits in an area. Now the absolute coolest thing about this is that you can actually go backwards. So in other words, if these two things are true, if 1 and 2 here are true, then we know that those first things are also true. Then there are no points in the exact same location, and all the points are randomly placed. So maybe I should call this A and B. A and B. No, I don't want A and B because I have, I'll say, what's good variables? Alpha and beta. There we go. That's okay. Then, so here is my alpha. Why can't it let me? Here's my alpha. Here's my beta. So it's saying if 1 and 2 are true. So if alpha and beta, alpha, beta imply 1 and 2. That's what this first part is saying. And this bottom part is saying 1 and 2 imply alpha and beta. So we can kind of do back and forth, which is really, really, really cool. So we'll stop here for this video. And in the next video, we'll look at an example, kind of where does this lambda come from? What does this kind of mean, etc. So we'll kind of see that in the next video. So I will see you then.